Good day, viewers. This is Ademola Johnson, your chemistry tutor and your biology tutor. Now, please don't forget to subscribe, share this video and like it. So, we have started talking about stoichiometry, and we have discussed a lot of things in stoichiometry. We have talked about the concept of mass, the concept of number of mole, the concept of volume, the concept of number of particles, ions and molecules. And we have started talking about, we talked about solution, standard solution and primary standard. So now we want to look at some calculations associated. So calculations associated with standard solution. Number one question I have here, which might not be can ask you, why is sodium hydroxide? Why is sodium hydroxide not suitably used in making a standard solution? Why can't we use sodium hydroxide to make a standard solution? Now, go with me. Let's look at some practicality of the answer to the question. Now, this is sodium hydroxide with me. Now, if we are to use it to prepare a standard solution, this is the weighing balance. Then, let me try to put it on. I have weighing balance, then let me, okay, it's at 0 now. Let me now try to do something here. You know, if I pour, what we are seeing there is sodium hydroxide. So what I have here now is 4.6 grams sodium hydroxide. Wash it closely and tell me what you will observe later. You will discover that after some time, the palette will now begin to have water, as if it is sweating. It is not actually sweating. What has happened to it is called deliquescence. It is a deliquescent substance. Why? Because on exposure to the atmosphere, it absorbs water and it dissolves in that water to form a solution. So now, if we are to use it to prepare a standard solution, the weight of the water it has absorbed from the atmosphere will also add to the weight of the solute, making it impossible for us to actually get the concentration of that solution. And another reason is that sodium hydroxide, now, they absorb carbon dioxide from the atmosphere also, because it's a lover of carbon dioxide. It combines with carbon dioxide to form sodium hydrogen triisocarbonate 4. So, and that's it. So, it's a lover of carbon dioxide. So, you can see there, it's just like when you have lime water. If lime water, which is calcium hydroxide, reacts with carbon dioxide, what does it form? It forms a milky solution, which is limestone, calcium triisocarbonate 4. The same thing here, but in excess now, it forms calcium hydrogen triisocarbonate 4. The same thing is happening here. Now, sodium hydroxide, being an alkali, reacts with the atmospheric carbon dioxide to form sodium triisocarbonate 4, which in essence forms sodium hydrogen triisocarbonate 4. So you might be thinking you are preparing a standard solution using sodium hydroxide, but actually what you are having there is sodium hydrogen triisocarbonate 4. That is why in our previous video, if you have not watched it, go and watch it. We said that one of the properties of a standard, primary standard, is that they are stable. They will not react with other things anyhow. They have high level of stability. So, and they are not deliquescent, they are not hygroscopic, they are not efflorescent. So, but because sodium hydroxide is efflorescent, and you can see it now, it's already sweating. It's already absorbing water from the atmosphere and dissolving inside the water. So because of that sodium hydroxide is not, and any other hygroscopic or deliquescent substance cannot be suitably used to prepare a standard solution. So if you see a question like this, they say, why? They ask you, there are two answers to this question that are seen here. They say, why is sodium hydroxide not suitably used in preparing standard solution? Number one answer, it is deliquescent. Number two, it absorbs CO2 from the atmosphere. And form sodium carbonate, which is no longer sodium hydroxide. So that is number one. Number two question, if they ask you, they say find the number of mole of 0.03 mole per dm cube of 250 cm cube Na2CO3. Then they now put Na equals to 23, C equals to 12, O equals to 16. And they give you something like this. What are they trying to do? Don't forget, this solution, when we prepared it in the last class, in the last video, we weighed 8.48 gram of Na2CO3, and we poured it inside this volumetric flask, and we added water until it gets to 1000 cm3. So, and when we calculated the number of mole, we got this. So this one is talking about the concentration of this entire thing. But where did we now see this 250 cm3? If I pour this one inside a measuring cylinder of the capacity of 250 centimeter cube. Look at this. This is a beaker now. If I add water if I pour it here now, and this one is graduated to 250. So this is 250 mil. Can you see 250 mil here? Written here. 250 mil here. This is 250 mil. So if I pour this inside here, to reach this mark, then I have 250 cm3 out of 1000 cm3 of this solution. I have poured 250 cm3. Inside this and this now, we still have 0.03 mole per dm cube, which is equivalent to what? Maybe 8.43 gram per dm cube. So that is what we mean. We have done similar calculation here in the previous video. You can watch out for them. Don't forget the formula to use is what? Number of mole. Number of mole is equal to what? Is equal to CV over 1000. Where your C is what? Concentration. Concentration in mole per dm cube. Mole per dm cube, which is also known as molarity. And V is volume. And that is what, according to the equation, 0.03 mole per dm cube. Then V is volume. Volume V, which is equal as what? In cm cube, which is already 250 cm cube. Now, then what do we do with that? Then we put in our formula. Our number of mole will now be 0.03 times 250, then over 1000. So what do we have? You can calculate that out to have, okay, we can have 0.03 times 250, then divided by 1000. So we have 0.0075. 1, 2, 3. Now move. So that's how to do that. So having done that, that's that. Then the next thing we have to look at is standardization. Standardization. What does standardization mean? Standardization means, this means the act of mathematically finding the concentration of a non-standard solution. The act of mathematically finding the concentration of a solution whose concentration is not known initially. Don't forget that a solution whose concentration is known is called a standard solution. Example. You can say, find the molarity of a solution containing 5 grams of NaCl dissolved in 300 cm3 of the solution. Yes. The compound here is sodium chloride, NaCl. Now, we don't know the concentration. Concentration is either in gram per dm³ or in mole per dm³. But rather, what we have here is 5 gram. Gram is the unit of mass, not the unit of mass concentration, since it does not have per dm³. So, this is, if 5 grams dissolves in 300 cm³, it's not a standard solution. For it to be a standard solution, 5 grams must be dissolved in what? 1000 cm³, which is the size of the volumetric flask. So you need to watch the previous video to see in part 5 of stoichiometry. This 300 is not up to 1000. So it is not a standard solution. So to standardize it, you will now interpret what we have here. You will say 5 grams of NaCl dissolves in 300 cm³. Then we are looking for S gram, the mass of NaCl that will dissolve in 1000 cm³ of the solution. Then what do you now do? You now say 5 over x is equal to what? 300 over what? Over 1000. Then what do you now do? Cross multiply. You have 300x is equal to 5 times 1000. So x will now be equal to, this one is 5000 now. 5000 over 300. 0, 0 goes. So you have x will now be 50 over 3. So we have 50 divided by 3. Answer is 15.67 gram per dm³. And this one shows, this means that 16.67 gram of NaCl dissolves in 1000 cm³, which is the same thing as 1 dm cube. So 1 dm cube is equal to 1000 cm. So this dm cube means what? So in every 1000 dm cube or 1000 cm cube, there is 16.67 grams of NaCl inside. Now, another where we have challenge is this. Now let's check. Now, another area of challenge is this. What if they ask you another example? So let's look at another example. If you ask, find the concentration of 5 grams per dm cube of sodium hydroxide solution in mole per dm cube. And they say sodium hydroxide solution, which is sodium hydroxide is NaOH. Now in mole per dm cube. Then they give us Na is 23, O is 16, then H is 1. How do we do that? The concentration is already in gram per dm cube, but they say they don't want it in gram per dm cube. They now want it in mole per dm cube. So what is your answer? What do we do? There is a formula. That formula is what? Molarity. Molarity is the same thing as molar concentration. Is equal to mass concentration over molar mass. Then, what's the molarity? That's what we are looking for. What's the mass concentration? That's 5 grams per dm cube. What's the molar mass? Na is 23. Oxygen is what? 16. Plus hydrogen is what? Is 1. So this gives us 5 over 23 plus 17. So what does it give us? 5 over, if we have 23, we have 23 plus 17. That's 40. So we have 40. So we have 5 divided by 40. The answer is 0.1213 mole per dm cube. So be careful. This formula wants to look like number of mole equals to mass over molar mass. But this one is molarity. That is molar concentration. It's equal to mass concentration over molar mass. And in another example, this is example 1. In example 2, what if they say find the concentration of 0.13 mole per dm cube of NaOH in grams per dm cube. And they also give us Na equals to 23, then O equals to 16, H equals to 1. We want to get this answer back. So what are we going to do? The same formula. We have molar concentration. Molar concentration equals to mass concentration over molar mass. Now, the molar concentration is already given to us to be what? 0.13. The mass concentration is what we are looking for. Mass conc. Then over molar mass. Molar mass is 23 for sodium. For sodium plus 16, which is oxygen, then plus 1. So we have 0.13 equals to mass concentration over 40. So what do we do? Cross multiply. Mass concentration will now be 0.13, which is this one, times 40. So our mass concentration will now be what? Will now be 0.13 times 40. And our answer is what? Our answer is 5.2, which is approximately what? 5 gram per dm cube, which is what we have here. So the bottom line of what we have done here is that if the concentration, this formula is used to change a mass concentration to a molar concentration and vice versa. So that is what it is for. So we are ending this section now. For now, if there's any question you need to ask, put it in the comment section and let me attend to it. So I remain my humble self, Afi Ademola Johnson. Don't forget to subscribe, share, and like the video. See you next time. God bless you, and bye for now.